I know you're a little bit of zoomed out, so to speak, of all of these online meetings. So I just appreciate you joining us for this one. I'm going to talk about the future projections of climate change for the South Central US. First, I want to recognize our funding from the USGS, University of Oklahoma's Office of the Vice President for Research, and the National Science Foundation, as well as our partners at NOAA's Geophysical Fluid Dynamics Lab. GFDL developed the climate projections you'll see, and they led much of the analysis of these projections in concert with our research team here at the South Central Climate Adaptation Science Center. Also, thanks to Dr. Adrian Wooten and Peyton Kavnar for creating the graphics for our projections. Before I dive into the projections, I'd like to get on the same page about what climate modeling is. You've likely used a model of some sort in your job. Models are meant to help us gain understanding about a climate system or just any system or concept. And here I list 5 broad categories of models, which is one of the reasons that people might misinterpret the term model. In many cases, the type of model that you use might be completely different than what somebody else uses. Statistical models are probably the most familiar type of model to many of you. Statistical models are powerful, but they don't explain why a process occurs. They are also limited by the data used to create them. Later in this presentation, I will talk about statistical downscaling. Our downscaling uses statistical models to relate regional climate to local climate. A global climate model, however, is a numerical model. Numerical models are comprised of mathematical equations that are translated into computer code. These equations calculate how variables change over time and can predict the future behavior of a system. Here's a subset of the equations that every climatologist learns in college. They represent laws and principles of physics, such as the conservation of energy, moisture, and momentum. These equations explain why things occur. And they can be combined with other equations to predict how the climate system evolves over time. So equations that describe physics, fluid motion, chemistry, and other things in our Earth system are coded into a global climate model, or GCM. In the GCM, the Earth is divided into millions of 3-dimensional grid cells, like a ginormous Rubik's Cube that's shaped like a sphere. These equations are solved for temperature, precipitation, wind, pressure, and other variables at each of these grid cells. GCMs use the world's largest supercomputers for months to compute the trillions of calculations for every time step, every variable, and every grid point until the end of the simulated century. Today's generation of global climate models can generate simulated tropical storms, jet streams, trade winds, and other major features of our climate, all simply from solving the physics equations that are forced by large-scale properties of our Earth system. These properties might include, or do include, what the concentration of different greenhouse gases are, where the continents and mountains are located, and how much energy is coming from the sun. GCMs describe the climate of a region. They do not predict the weather at a specific place. So they don't tell you what to wear on a given day, but instead they suggest what your wardrobe should be for that area and that decade. And while no model can exactly reproduce our complex climate system, GCMs produce meaningful results that have been shown to be representative of Earth's climate after we input that concentration of atmospheric greenhouse gases. So now let's look at what global climate models tell us about changes in the Earth's climate. Let's examine a few scenarios that we use to examine possible futures. Scenarios anticipate possible future changes in emissions and other radiative forcings to our climate system. We don't have observations of how greenhouse gases will change in the future, so we need to generate several emissions pathways that may be possible given choices that societies can make for the future. There are three commonly used scenarios called RCP 2.6, 4.5, and 8.5. RCP stands for Representative Concentration Pathway, and it's a time sequence of how our climate would change if extra energy is trapped in the atmosphere. RCP 8.5 represents an increase in greenhouse gas emissions until the end of the century, where it adds 8.5 watts per meter square of energy across every square meter on Earth's surface. It's typically called the business as usual scenario, and it's the direction we are currently headed. RCP 4.5 represents a stabilization and reduction of emissions around 2100 using a variety of technologies and strategies. RCP 2.6 is a peak and decline scenario where greenhouse gas emissions are reduced significantly by the next decade and beyond. We plug each scenario into the 20+ global climate models, and they do their months and months of calculations. And then we analyze the changes in those climate variables over time. For example, we see that for RCP 8.5 in the red line, the models project that by the end of the century, our globally average surface temperature will be 3 to 5 degrees Celsius warmer than in the past 30 years. RCP 2.6 in the green, the globally average surface temperatures are projected to be 0 to 1.5 degrees warmer than the recent past. So clearly the scenarios make a difference. That means that when you look at global climate model projections, you need to read both the time frame of the projections and what scenario the projections are generated from. Here the maps display the change in surface temperature by the end of the century as compared to the recent past, with RCP 2.6 on the left and RCP 8.5 on the right. In both cases, temperatures increase globally, with substantially larger increases in the 8.5 scenario. We can also look at projected changes in precipitation, in this case for RCP 8.5 by season. There are other variables that the global climate models output, but we will focus on temperature and precipitation related variables in this presentation. Now that we have output from the global climate models on a large scale, we want to make sure that the output is more meaningful to you as a local decision maker. So to do so, we downscale the GCM output to a higher resolution grid. In our case, we use statistical relationships between long-term historical measurements at local weather stations and that larger scale GCM output. For example, the global climate model may have a grid spacing of 100 kilometers by 100 kilometers. And using statistical techniques, we can downscale to a grid spacing of perhaps 10 kilometers by 10 kilometers. It's especially important to downscale the GCM output when you have local questions and where you have mountains, coasts, urban areas, or other major spatial changes. Downscaling helps to localize the climate projections so that you can have information better suited to your needs. At the South Central Climate Adaptation Science Center, we use an ensemble approach to develop climate projections for the South Central United States. This approach uses multiple scenarios, multiple GCMs, multiple downscaling methods, and those are trained on multiple observational data sets. And this produces a large number of downscaled climate projections for daily maximum temperature, daily minimum temperature, and daily precipitation. The resulting downscaled projections over the South Central US have a 0.1 degree latitude by 0.1 degree longitude resolution. And this gives you essentially a 10 kilometer by 10 kilometer grid spacing. Our three scenarios that we use are RCP 2.6, 4.5, and 8.5, giving us a range of societal responses to climate change. We use three global climate models that have been analyzed for our region and were shown to produce a representative climate historically. Each downscaling method was trained using three different observational data sets that are heavily used in climate-related research. And finally, the three downscaling techniques that we chose are of different families of techniques that have been widely used throughout the literature. They don't represent every downscaling approach, but each has unique features that make them useful in different situations. In the end, our ensemble-based approach results in 81 climate projections for each of our three variables. So I mentioned before, our three core variables are daily maximum temperature, daily minimum temperature, and daily precipitation. And frozen precipitation amounts are converted to their liquid equivalent in regions where you have snow or ice. But from these three variables, we can generate a host of derived variables because we have the daily output for over 100 years. Some examples of these derived variables include the count of the number of days during a given time period when we have days over or under a certain temperature threshold, such as 100-degree days or hard freezes. We can do the same with thresholds of precipitation amount, like the number of days with 2 inches or more of rain. We also can look at specific types of events, like the length of dry spells or the maximum rainfall in a consecutive 5-day period. For each variable, the 81 projections are sorted into the 3 RCP scenarios. So this leads to 27 projections for each scenario and variable. Okay, so now on to what you've been waiting for. I'm going to show you a sampling of our products. We're in the midst of finalizing our products, and we'll be placing them on our web pages for you to use. The maps that I'm showing you have a lot of commonalities, so let me walk you through them. First, all of these maps are averages of the 27 projections. Doctors Adrian Wooten, Derek Rosendahl, myself, our colleagues at GFDL, and others are looking at the full set of projections for each product to help guide you in interpreting that product. But for simplicity, you'll just see the ensemble averages here for 2 scenarios. On the left is RCP 2.6, the low scenario, and on the right, RCP 8.5, or the high scenario. Now, each map identifies the projected change in a given variable. These change maps show the difference between the future period and our recent historical period, which is from 1981 to 2005. Here, the future period is the mid-century from 2036 to 2065. So you're looking at the projected change in the annual average low temperature across the South Central US by mid-century in the peak and decline or low scenario on the left, and the business as usual or high scenario on the right. The results indicate that in the low scenario, average low temperatures across the region are projected to increase by 1 to 3 degrees Fahrenheit by mid-century. And in the high scenario, average low temperatures are projected to increase from 4 to 6 degrees Fahrenheit by mid-century. The increases are smaller near the Gulf Coast and increase gradually as you move northward. By the end of the century, 2070 to 2099, the difference in the 2 scenarios is quite large. If societies choose to quickly and significantly respond to climate change, we can keep our average low temperatures to only 1 to 2 degrees Fahrenheit warmer than today. But if we continue on our current course, average low temperatures are projected to be 6 to 10 degrees Fahrenheit warmer than our recent past. Clearly, we would have more adaptation to do in the high scenario than in the low scenario. I do want to mention here that our level of confidence in these temperature projections is very high. There is a straightforward relationship between more energy added to our atmosphere through adding greenhouse gases and higher temperatures. Also, our 21 projections for these and the other temperature-related maps that I'm going to show you are extremely consistent. That means that no matter what combination of global climate model, downscaling technique, or observational data set that we use, we get essentially the same results. And these results are also consistent with those of the National Climate Assessment, which use an entirely different downscaling technique and more GCMs. The next maps will show the projected change in the annual average high temperature. We see a similar story to the low temperatures. By mid-century, high temperatures are projected to average 1 to 6 degrees Fahrenheit warmer than the recent past. Again, the Gulf Coast sees the least change, with the Navajo Nation and the north-central portions of our region seeing the greatest change. By the end of the century, the difference between the 2 scenarios, again, is stark. with high temperatures averaging upwards of 10 degrees Fahrenheit warmer than the recent past in northern Kansas in RCP 8.5. We can slice our data by season also. The top row shows changes for mid-century, and the bottom row shows changes for end of century. We define the seasons climatologically, so winter is December, January, and February. Spring is March, April, and May, and so on. All of these images are for the high scenario, or RCP 8.5. While temperature changes are similar year-round, we unfortunately see that the greatest changes are during the summer, both in the mid-century and in the end-of-century projections. The next product is the projection of the change in the number of days when the high temperature is warmer than 100 degrees Fahrenheit. These are the days that I just hate. I wish the projections showed them just going away. But even in the low scenario, we are projected to have about 20 more days across much of Kansas, Oklahoma, and Texas, as well as southern New Mexico. For the high scenario, portions of southern and southwest Texas are projected to have over a month more of days over 100 degrees Fahrenheit. If there's ever a map to convince you to make changes now in the face of climate change, I would think this one would be it. In the high scenario, the projections indicate 1 to 2 months more than we've already experienced on average of days over 100 degrees Fahrenheit. Recall that we are very confident in our temperature projections. These high temperatures can undoubtedly stress both natural and agricultural ecosystems, water supplies, wildlife, and human bodies. And today's college students will be grandparents during this time frame. Now let's turn our attention to precipitation. This product shows the projected change in yearly precipitation that the region receives on average. Change values are in percent change from the recent past to the mid-century. So negative values indicate that our total annual precipitation will decline in the future. Total precipitation may affect the amount of water stored in a reservoir, but typically people are more interested in the timing of the precipitation during the year. So this product might not be as helpful to you as some of our other products. We see that parts of the Great Plains are projected to dry by about 10% in the high scenario, and there's little change in the low scenario. However, the ensemble average may not be a good indicator of the range of projections that we have. Here's what I mean. At the top is the ensemble average for RCP 2.6 that you saw in the previous slide. The 27 projections that were used to create the ensemble average fill the rest of the screen. They are grouped by the global climate model that they were downscaled from. It is clear that the GCM has a heavy hand in the precipitation projections, and not every GCM projects the same direction of precipitation change. For temperature, the relationship between adding greenhouse gases and heating our atmosphere is direct. However, precipitation has lots of ingredients. Temperature projections are like making scrambled eggs. Even I can do that. Precipitation projections are more like making a souffle. In some regions of the world, like the Northeast and Southwest United States, most of the models agree on the direction of change. Unfortunately, in many parts of the South Central United States, different GCMs will produce different results for precipitation, some wetter and some drier. This example is one of the reasons that we encourage folks to partner with a climate boundary organization, like the 3 that co-host the science series. In that way, we can help you interpret the products according to the types of decisions you'd like to make. In some cases, these differences in projections won't matter for your location or decision. And in other cases, they may be really, really important. So back to the mid-century map. Although the projections for RCP 2.6 ranged a bit from the Ensemble Average, it turns out that the range is not as large for RCP 8.5. So most of the projections for RCP 2.5 showed less rain or snow in much of the western part of our region, though they disagreed a little bit in the amount. Our next map shows the projected change in the annual average number of days with at least 1 millimeter of precipitation. We call these rain days, even if there's snow involved. With the annual precipitation product, all of the rain could have come on a single day. Here, we get a better idea of how many more or less days we would have with rain. So in RCP 2.6, we see that there's not much of a change in the average number of rain days by mid-century. But in RCP 8.5, we see an average decrease of 2 to 5 days in measurable rain across much of our region. Similar to what we saw for mid-century. Sorry, I got behind on one product. Similar to what we saw for mid-century, the low scenario for the end of the century shows only a few more or several fewer rain days as compared to the recent past. The 27 projections that are averaged for the left panel have different locations of where the higher and lower values of change are located. So our confidence in the locations of the light yellow and light purple regions is low for RCP 2.6. On the other hand, with the exception of Louisiana, the projections for the high scenario consistently indicate that there will be 5 to 15 fewer days on average. One of the GCMs shows a slight increase in rain days in Louisiana, and the other 2 show slight decreases. So our confidence in this product for New Mexico, Texas, and Oklahoma is fairly high, but it's relatively low for Louisiana. Now we're looking at the number of days with precipitation greater than 2 inches in a single day. These situations can be potentially damaging, especially with flooding in low-lying or poorly drained areas. In comparison to the last product, these change maps have more consistent patterns in both the low and high scenarios and in both mid-century end of century timeframes. So our confidence level is moderately high for these projections. The western half of the region is projected to see little or no change in these heavy rainfall days. However, the eastern half is projected to see 1 more day of 2-inch rainfall at least every other year by the middle of the century. For the end of the century, the Texas Gulf Coast is projected to experience another day on average each year with 2-inch rainfall or more in the low scenario. In the high scenario, far eastern Oklahoma and northern Arkansas are projected to see at least 1 more day on average annually of these heavy rainfall events. These results are important for long-term planning, such as the construction of stormwater management facilities. Our last product for this presentation is the projected change in the maximum rainfall that occurs over any 5-day period during a year. These events tend to result from either slow-moving tropical storms near the Gulf Coast or multi-day mesoscale convective complexes that travel from the high plains into eastern Oklahoma and western Arkansas, where they can stall overnight. These events can bring extensive flooding across a broad region. Here we're looking to see if these multi-day events will dump more rain or less rain on us in the future. For the mid-century, we see two regions highlighted in both the low and high scenarios. Both of these coincide with the locations I just mentioned. Along the Gulf Coast, the results indicate an increase to 1/2 to a full inch of rain on average for the annual maximum 5-day rainfall period. The 27 projections demonstrate a moderate level of consistency for this Gulf Coast projection. In eastern Oklahoma and western Arkansas, however, the 27 projections do not agree. In some cases, they show a decrease in the amount of rainfall for these events, and in other cases, a large increase. So we have low confidence in that region, whereas we have moderately high confidence for the increase along the Gulf Coast. In the end of century projections, we see the Gulf Coast and southern Texas are projected to see more rain during these maximum 5-day rainfall periods each year. Some places may average more than 1 inch of additional rain during these high-end 5-day events. And although there's a large blob in Arkansas in the high scenario, not all of the models and downscaling techniques agree on this bullseye. We have more products, but I'm going to stop here. I remind everyone that climate projections are not forecasts or predictions like we're used to seeing on our weather apps or TV broadcasts. It's important to work with a climate scientist to make sure you're applying the projections correctly to your situation and you're interpreting the output appropriately. As you get familiar with the projections, the interpretation does become easier. Also remember that with our products or any other climate projection, climate scientists have higher confidence in temperature projections than in the precipitation projections. But for our region, even if you aren't sure about the precipitation projections, we know that soils will dry and ecosystems will become stressed as warmer temperatures lead to higher evapotranspiration, even if the amount of precipitation stays the same. Our team is working to get our data files, maps, and other graphics ready to use. We were hoping to have them all online by today, Earth Day, but the pandemic took a little wind from our sails. As we add the products, we'll let you know on our Facebook and Twitter feeds, so make sure that you follow us there. And if we have time, I or other members of our South Central Climate Adaptation Science Center research team are happy to answer your questions.